Hi everyone, welcome to Unit 28 of online course on probability distributions. In this session, we are going to discuss hypergeometric distribution and its approximation to binomial. That is, how the hypergeometric distribution is associated with the binomial distribution. Already we have defined hypergeometric distribution and its probability mass function, mean, variance, etc. in the last session. We know the hypergeometric distribution is defined with respect to a population that consisting of two types of items. That is, suppose we have a population having two type of items, type 1 and type 2, and we are selecting items from this population, and suppose the population consisting total n items, of which m are of type 1 and n minus m are of type 2. So this is the background, that is a population consisting of n items of two types, type 1 and type 2, and type 1 there are m items and type 2 there are n minus m items. And what we are doing, we are selecting n items are selected without replacement. Okay. So we are selecting n items from the population and that are selected without replacement. So our question is, what is the probability of getting k items of type 1? That is, suppose we are finding what is the probability of k items of type 1. So x be the random variable defined as number of type 1 items. Suppose we define the random variable x as number of type 1 items. So our problem is finding the probability of x is equal to k, that is equal to, see, we have the population having n items and from this we are selecting n items. So the total ways is nc and possible ways are there. And we have m items of type 1 and we are selecting k items. So there are possible mck possible cases. Okay. And of course there are n minus m items of type 2, and if we are selecting n items and we are assuming there are k items of type 1, there will be n minus k items of type 2, and that is possible in n minus m c n minus k times. So these are the background, that is we have n items and we are selecting n small n items from the population. Okay. And there are nc and total ways. And we have m type 1 items and we are selecting k items. So there are mck total ways favorable to that k type 1 items. And the remaining n minus m items, total items are there, and we have small n minus k of type 2. So favorable case for that type 2 items are n minus m c n minus k. So what is this probability? This probability is mck n minus m c n minus k divided by NCN. Of course, this value k is any value from 0, 1, 2, etc. And the maximum value is minimum among the value n or capital M. Because capital M is the type 1 items and we are selecting n items, which one is the minimum of that one? That is taken as the maximum value of this k. Okay? So, probability of x is equal to k is this one. And this probability we call it as hypergeometric probability mass function of the random variable x. Now, the question, actually this is a situation that arises when we considering dichotomous population, a population that is divided into two classes. And in the case of binomial distribution, we know binomial distribution is actually, it is a distribution or it is a probability model that is obtained when we are considering Bernoulli trials having either success or failure outcomes with a constant probability of getting success throughout the trials, and you count the number of successes obtained out of n trials, then probability of getting a certain number of success is obtained by the binomial probability mass function value. So, similar, the situation is similar, the only difference is in this case we are considering without replacement, that is the probability will be different in each trial getting a success or getting type 1 items. But in the case of binomial distribution, the probability of getting success is constant throughout the trials. So, the basically our question here is what association or how can you approximate this hypergeometric distribution to binomial, because binomial distribution and hypergeometric distribution are associated with the same type of population, dichotomous population, success and failure or defective or non-defective items, literate or illiterate or male or female, that classification. So, our problem is to identify the condition, the limiting condition by which this hypergeometric distribution tends to binomial. So, we are going to discuss that case, that one here. So, this is the situation. Let x be a discrete random variable with a probability mass function, and already I have given the probability mass function. This is the probability mass function value, and now we are establishing that this hypergeometric distribution tends to binomial as the number of items in the population is large, that is capital N is large. This is actually total number of items in the population, and m divided by n. What is m? M is actually type 1 items are, number of items are m, and type 2 items are n minus m, and total items are n. So, if we have the ratio m divided by n is approximating to a constant, that is we call it as p, and that is m divided by total number of, type 1 items divided by total number of items is approximating to a constant value p, then on the basis of these two conditions, hypergeometric distribution tends to binomial. See, consider probability of x is equal to k here, and that is m c k n minus m c n minus k divided by n c n. Okay. This is the probability mass function. Now, you consider this m factor, this is actually m factorial divided by m minus k factorial into k factorial, that is the mck, and n minus m is n minus m c n minus k is n minus m factorial divided by n minus m minus n plus k factorial. Okay, this n minus m minus n minus k, that is minus n plus k factorial, that divided by n minus k factorial. So, that is about the numerator value, whole divided by NCN. NCN is n factorial divided by n minus n factorial into n factorial. So, that this is actually simplification of the probability mass function based on the definition or the value of NCR. NCR is n factorial divided by n minus r factorial into r factorial. Based on that, we have this expansion. So, the steps here, this is the first step we have, that is probability of x is equal to k, hypergeometric distribution value is given here. Then we have the simplification like this, and then after this we have we expanded the NCR and cancelling the common terms, you will get like this. Then you try to make all the expressions in terms of m divided by n's, and the expression is like this. We have the expression m divided by n, m divided by n minus 1 divided by n, etc. up to m divided by n minus k minus 1 divided by n. Then 1 minus m divided by n, 1 minus m plus 1 divided by n, etc. up to 1 minus m plus n minus k minus 1 divided by n into 1 divided by 1 minus 1 by n, 1 minus 2 by n, etc. up to 1 minus n minus 1 divided by n. That is actually, it is obtained by making the expressions in terms of m divided by n's and 1 by n's. Okay. And after this, we apply the condition n tends to infinity and m divided by n tends to p, then this is the value. And so, we proved that hypergeometric distribution tends to binomial probability mass function value when applying the condition n capital N tends to infinity and m divided by n tends to p. So, this is the proof related with the hypergeometric distribution and binomial association between binomial distribution. And before going to the next details, let me just give the expression for the recurrence relation of the hypergeometric probability also. It is also very easily established by just substituting the probability mass function of the hypergeometric probabilities. So, let x be a discrete random variable with a hypergeometric probability mass function, then we can write probability of x is equal to k plus 1 divided by probability of x is equal to k like this. So, we have the probability ratio between probability values of x is equal to k plus 1 and x is equal to k, that is equal to n minus k into m minus k divided by k plus 1 into n minus m minus n plus k plus 1. And this expression is very evident. Just to substitute the probability values, you can have the probability, values. This is the probability value of x is equal to k, that is hypergeometric probability mass function, and replace k to k plus 1, we have the second expression. And so, you find the probability of x is equal to k plus 1 divided by probability of x is equal to k, that is the right side expression of this one is divided by this one, and replace the MC, k and other combinations NCN etc. to using the expansion of NCR. NCR is equal to n factorial divided by n minus r factorial into r factorial, and based on that expression, you substitute the actual values here, and cancelling the common terms, our value will be this one, probability of x is equal to k plus 1 divided by probability of x is equal to k is equal to n minus k, capital M minus k divided by k plus 1 into n minus m minus n k plus 1. So, this is only a very simple algebra. Algebra is required, only cancelling the common terms you will get the result. So, this is another aspect with respect to hypergeometric distribution probability mass function, that is the ratio between probability values of x is equal to k plus 1 and x is equal to k. And before concluding this session, let me give very interesting applications of hypergeometric distribution. So, hypergeometric distribution is usually used to find the unknown number of items. Suppose we have discussed the population size capital N, that is the population consisting of capital N items. So, how do you use the hypergeometric distribution to identify the value or to estimate the value of n if n is unknown? So, that is one of the applications of hypergeometric distribution that is usually used in physics in some practical purpose. And suppose that number of type 1 object is known, that is m is known. Suppose we have already discussed the total items, total n and type 1 m and type 1 m and type 2 n minus m. Okay. And suppose this is unknown to us. Suppose the number of type 1 object m is known. This is known to you. This is known. And if it is known, how do you estimate the value of capital N? So, this type of problems usually arises in the field of estimating animals in a forest or estimating fish in a lake, etc., in some that biological some problems. So, how do you use this hypergeometric distribution? So, to estimate the size of animal population, we are using the concept of hypergeometric distribution, and that problem is usually known as capture and recapture data. The method of estimating the size of animal population usually known as capture and recapture data. And in this context, the estimation problem is sometimes called the capture recapture problem also. So, for an example, you consider a lake containing capital N fish. Okay. So, we have a lake, and as an example of this type problem, suppose that we have a lake containing N fish, and this N is unknown. Okay. The lake containing we have N fish, but that N is usually unknown to us. How do you estimate, approximate the value of capital N? And for that, you make that population similar to a population associated with the hypergeometric distribution. And that is what we are doing. We capture M of the fish, you select some of the fish, capital M fish are selected, and tag them and return to the lake. Okay. So, from the lake you capture a small number of fish M, and tag them and return to the lake again. So, M is the total number of tagged fish in the lake. So, M is the total number of, N is the total fish, total number of fish in the lake, and M is the tagged one. And of course, you just look, and this total number of fish are two categories now, that are either tagged one or non-tagged one. So how many are not tagged? That is n minus m. So this is a population having m items of first type and n minus m items of second type. So then what we are doing, we capture n of the fish and observe x. So we have capture n fish again. And out of this n fish, how many are tagged? That you can see. So suppose x is the tagged fish. Already we have in the lake tagged fishes are there and non-tagged. And out of the total n fish selected, suppose x are the tagged fish. So x divided by n, we call it as sample proportion of tagged fish. It is a sample proportion of the tagged fish. And what is the population proportion of the tagged fish? M divided by n. Because we have total m fish, tagged fishes and total n fishes are there. So that is in the lake, the proportion of tagged fish is m divided by n. So what we are doing, we are approximating these two. Equal to, the sample proportion is approximately equal to the population proportion. X divided by n is equal to m divided by n. And from this, see, our problem is what? The problem is to find the capital N. What is capital N? Capital N is obtained by equating x divided by n and m divided by n. That is, the estimator of n is obtained by equating sample proportion to population proportion. That is, x divided by n is approximately equal to m divided by n. Hence, capital N is, this is, you just note, this n is equal to n into m divided by x. So this is an application usually used in the field of this type of matters, that is identifying the total number of animals, a particular number of animals in a forest or fish in a lake, etc. So capital N is estimated as n into capital M divided by x. The only matter we have, m is the tagged fish, total tagged fish, and n is the fish selected, and x is the among the selected fishes, how many are tagged. So this is one of the applications of hypergeometric distribution. And again, we can use the hypergeometric distribution in the second situation, that is, suppose the size of the population n is known, that is, total number of items are known, but the number of type 1 object is unknown. That is, capital N is known here, that is, we have the population, capital N is the total items, this is known. But type 1 items, suppose we have type 1 or type 2, whatever it is. Type 1, suppose m is the number of, that is unknown. So capital M is unknown. Suppose the size of the population is known, but the number of type 1 object M is unknown. This type of problem usually arises in an industry, some type of, that is production industry. So this type of problem arises, suppose you have n items are manufactured, that is known. So total 1000 items are manufactured. But we want to know how many are defectives among this total items produced. And this is practically impossible to identify all the items, whether it is defective or not. So how the management or how the industry people are identifying approximate number of defective items produced by that machine or that production unit. So here the problem is estimating the type 1 object, or type 1 means here it is defective. So how you are identifying that? That also can be addressed using the concept of hypergeometric population. So why we are not possible to identify all the items? It would be too costly to test all the items, or perhaps even destructive. So we might instead select some items from the production unit, and from that items you identify how many are defective. On the basis of that number, we are approximating the total number of defectives. So what we are doing here? Suppose x of n selected items are defective. See total n is known here, and we select n items from here and identify how many are defective. Suppose x are defective. X are defective from of this n items. Okay, a production unit manufacturing n units, of which n small n number items are selected, and of this you identify how many are defective, x are defective. Let us estimate the number of defectives out of the total manufactured items by equating sample proportion of defectives to population proportion. Okay. So let us estimate the number of defectives out of the total manufactured items by equating sample proportion to population proportion of defectives. So that is x divided by n is the sample proportion of defectives, because we have n items selected of which x items are defective. So this is our sample proportion of defectives, and we have total n items, and let m be the total defectives. So m divided by n is the population proportion. Hence what we are doing, you are approximating that values, equating the values. So that is our value m is obtained by n x divided by n. That is the total number of defective items produced by that production unit is equal to capital total n items into the items, defective items obtained from n selected items. So this is the usual practice followed in order to identify the total defective items produced by a production unit in a manufacturing unit. Or suppose we are interested to know total number of items in a, or total number of animals in a forest, or total number of particular type of species in a forest, etc. So these are the some applications usually we used in some practical situations based on the hypergeometric concept. So these are the details with respect to the hypergeometric distribution, and some more numerical examples we can work out in the succeeding sessions. So thank you for listening this session. Thank you once again.